Now in this we are going to have the definition of conjugate points and conjugate lines with respect to a parabola as well as with respect to an ellipse. So first we see this result. It states that if the polar of a point P of x1, y1 with respect to a parabola passes through a point Q of x2, y2, then the polar of Q with respect to the same parabola will pass through P. So if we have 2 points, say we have x1, y1, we consider P of x1, y1, that is 1 point, and we consider another point, say Q of x2, y2. We say that these 2 points are conjugate points provided the polar of this P passes through Q, and in this result of course we are going to show that the polar of Q will pass through P. So these 2 points in that case will be called as conjugate points. So for that first we will establish this result. So we consider 2 points P of x1, y1 and Q of x2, y2. So the polar of this will be y1 is equal to 2a into x plus x1, and if it passes through the point, so suppose this is the polar of P, say, then it passes through the point Q of x2, y2. So the equation is this, and because it passes through x2, y2, we have this equation. Now we consider this point Q of x2, y2. See, the polar of that will be, you have, suppose this is the polar of this, and the equation will be what? Y2 is equal to 2a into x plus x2. So in order that this has to pass through this, if we replace x and y by x1, y1, something is to be true, but that follows because of equation 1. So polar is given by this, and it is obvious from 1 that the polar of Q passes through P of x1, y1. Now the condition for 2 points x1, y1 and x2, y2 to be conjugate points with respect to a parabola y square equal to 4ax is just y1, y2 is equal to a into x1 plus x2. So next we have this definition. If the polar L, I have this polar L, that line of P of x1, y1 with respect to a conic, let it be parabola or ellipse or hyperbola, whatever may be the conic. If the polar L passes through Q, then the polar small l, if I denote it as small l, polar is always a line, it passes through polar L of Q with respect to the same parabola will pass through P. That is the result that we established now. So these 2 points are called conjugate points. 2 lines are said to be conjugate lines in a parabola with respect to the parabola if the pole of the first one lies on the second line and vice versa. So if the pole of one lies on the other, so then see we have conjugate points and conjugate lines as well as. If we have the figure, from this we have the definition of both conjugate points and conjugate lines also. The pole of one should lie on the other and vice versa. Okay, so in that case then we call those 2 lines to be conjugate lines. This condition for 2 lines to be conjugate with respect to a parabola can be obtained by using the definition. So the condition is this. You are given 2 lines, L1x plus M1y plus N1 equal to 0, L2x plus M2y plus N2 equal to 0. So these 2 lines will be conjugate lines provided some condition is true. So how to obtain the condition? Given any line, we know how to obtain its pole. The definition says that the pole of one should lie on the other line. Only then those 2 lines will be called as conjugate lines. So L you consider as L1, capital L1, this line, capital L2, this line. Now let us assume that these 2 lines to be conjugate lines, only then we can obtain the condition. So you first find the pole of the first line. This is what you get. In general, Lx plus My plus N equal to 0. For that, pole will be N by L minus 2am by L. So here we have L1, M1, N1. So this is what we have as the pole. The pole of this should lie on the second line. So just substitute in the place of x and y these values, and on simplification this is what we get. L2 N1 plus L1 N2 is equal to 2a into M1 M2. So that is the condition for two lines to be conjugate lines with respect to a parabola. Now, in the case of ellipse, the definition we said already that conjugate points and conjugate lines with respect to a conic. So, the same definition holds. Now, we arrive at the condition. We are given two lines, Lx plus My plus N equal to 0, L prime x plus M prime y plus N prime equal to 0. Now, procedure is the same. You obtain the pole of the first one, it is minus La square by N minus Mb square by N. It should lie on the second line. So replace your x and y by these two, and on simplification you get LL prime A square plus MM prime B square is equal to NN prime. Next we have the definition of conormal points. Now any 3 points on a parabola. So 3 points that we consider, any 3 points on a parabola, the normals at which pass through a common point. Then you call this P, Q, R to be conormal points. So any 3 points on the parabola, the normals at which pass through a common point. So then we call these points to be conormal points. Now we have this result which states that in general 3 normals can be drawn from a given point to a parabola, and the sum of the ordinates of the feet of the normals is 0. Now how to obtain this? 3 normals. See, just because we have drawn 3 lines, that why can't we draw 4 lines, 5 lines? All that questions will arise. For that only we have this answer. We have the parametric form of equation of normal to be y plus tx is equal to 2at plus at cube. Now suppose it passes through the point hk. Then replace your x and y by h and k. So this is what you have. Now rewriting that, you have at cube 2a minus h into t, then minus k. You are taking the whole lot to the other side. So this is what we get. Now this is a cubic equation on T, and therefore should have 3 roots T1, T2 and T3. So that is the reason why we conclude that 3 normals can be drawn from any point, and we can only draw 3 normals from that particular point, and that's because of the cubic equation that we have when we consider the parametric form. Right. Now having got the cubic equation, and by assuming that T1, T2, T3, so being a cubic equation, it will have 3 roots, let them be T1, T2, T3. Then from theory of equations, we know the relation between roots and coefficient. Relation between the roots and coefficients. Using that, we have these 3 equations. Sum of the roots, this is nothing but sum of the roots, and this is nothing but sum of product of the roots taken 2 at a time. And this is product of the roots. So this is from the theory of equations. We have this T1 plus T2 plus T3. There is no T square term. T square term illa அப்படிங்கிறதுனால 0 into T square. So you get 0. And product of the roots, sum of the product of the roots taken 2 at a time. Coefficient of T and that divided by A. I mean the coefficient of highest power. And the last one, see, always when you write the relation between roots and coefficients, sum of the roots will be minus, then plus, then minus, plus, minus, it will go on and on. So here already one minus sign, and in this case third one, so minus of minus, so k by a. Now you consider the sum of the ordinate. Ordinate means what? When we consider x and y, you know that this is called abscissa, and this one is called ordinate. The y coordinate is called as ordinate. So you have abscissa and ordinate. Here some of the ordinates. So when we consider t1, the meaning of it, at1 square to at1. And similarly for t2 and t3. So sum of the ordinate means what? It is 2at1 plus 2at2 plus 2at3. Adanudaiya sum. So 2a can be taken out, t1 plus t2 plus t3 you have, but that is 0, so you get 0. Now this theorem and the following one repeatedly they will be used. So if what is the statement? If the normal at the point t1 meets the parabola again at the point t2, the relation between t1 and t2 is, this point is taken as t1, this point is taken as t2, this one and this one. So if the normal at t1 meets the curve again at t2, then t2 is given by, this one is given by minus t1 minus 2 by t1. So that is what we are trying to prove. Now how we are going to prove that? So you write out the equation of the normal at t1, and you also write out the equation of the chord joining t1 and t2. Both represent the same line only. When I consider this, this is the normal. I can view this as, if I name it as PQ, this can be viewed as first normal at P. The same thing can be viewed as the chord joining. Okay, the same thing can also be viewed as chord joining PQ. Okay, P and Q. So, adhanuடைய equation இப்படி இருக்கும். அதிலிருந்து you can write out the you can identify, because both of them represent the same line, you can identify them. When we do so, this is what we get, and from these two itself we are getting what is required. So 1 by t1 plus t2 is equal to minus t1 by t2, and that in turn implies this, which in turn gives t2 is equal to minus t1 minus 2 by t1, to be remembered always. Now the next one is, if the normal at the 2 points, see we have one point to be t1 and another point t2. In the previous case, the normal at t1 met the curve again at another point. So we had the relation between these two. But here what we have is the normal at t1 and normal at t2, both of them meet the curve again at another point r. So if that is the case, you have to show that the product of these two, that is t1 and t2, is 2. So there are two methods. In the first method, we have this one is the third normal, the third point on the curve. So let the normals at P of t1, Q of t2 intersect at R of t3. Then PQR will be conormal points. Definition badi, இதுங்க மூணுத்துக்கும் பேரு conormal points. இந்த conormal points வந்தாலே all these conditions will be true. Whatever we have mentioned here, they will be true. This one and this. So it is this that we are going to use. இப்போ இதுங்க இந்த கேஸ் எப்போ வருதுன்னா, all of them meet at one point HK. But இந்த இடத்துல all of them meet at the point HKக்கு பதிலா AT3 square 2AT3 ன்னு இருக்கு. அப்போ wherever you have T3, K, you can replace it by 2AT3. So we consider the fifth equation, and in that K is replaced by 2AT3, and cancelling out T3 because it's non-zero, and Ka can also be cancelled. You have this. This is one way. Another method is, just now we proved that whenever the normal at T1 meets the curve at T3 means the relation between T3 and T1. So that is T3 is minus, you have T3 to be minus T1 minus 2 by T1. So in the same way, the normal at T2 meets the curve again at T3. So you have T3 to be minus T2 minus 2 by T2. The LHS being the same, we can equate the RHS. So this is what we get. Then taking this to the other side, T2 minus T1, and then taking this to the right side, this is what we get. This on simplification. Okay, so T2 minus T1, you can cancel out this, and then cross multiplying you get T1 T2 to be equal to 2. So these two problems are very important when we do further problems in the worked out problems category, these two theorems. So in the worked out problems or in the exercise problems, we need to remember this result. T2 is equal to minus T1 minus 2 by T1. The other one, T1 T2 is equal to 2. Now in which case we have which condition, that we should be very familiar.